In the first sum, we need to prove that triangle ABC is similar to triangle ADE. In order to do that, we need to find two sets of corresponding angles. As we can see here, we have vertically opposite angles CAB equals to EAD as seen from the arrangement CAB EAD, and the alternate angles CBA corresponding to EDA, alternate angles, parallel lines BC parallel to DE. Thus, ABC is similar to triangle ADE, and the reason is because we have two sets of corresponding angles AA. Once we have done that, we will need to get the known ratio, which is from the pair of known sides AC. Since AC corresponds to AE, therefore the ratio is AC over AE, giving us 2 over 3. In similar triangles, any pair of corresponding sides will give you the same ratio. Therefore, the corresponding sides AB corresponding to AD, which is x over 4, will be equal to the same ratio 2/3. And cross multiplying, we have x equals to 2 and 2/3. Similarly, the corresponding sides BC over DE, or y over 10, is also equal to the same ratio, and once again we cross multiply, giving us y equals to 6 and 2/3. In the next part, we have to prove that triangle ABC is similar to triangle ADE. This is easy because we have corresponding angles because of the parallel lines. And once we have proven that, again we find the known ratio from the pair of corresponding sides which are known, that is AC corresponds to AE. So AC over AE. AC is 8 and AE is 10. We reduce it to 4/5. Thus, the corresponding sides BC over DE, BC over DE, or x over 12 will be equal to the same ratio. And cross multiplying, we have x is 9 and 3/5. Similarly, the corresponding sides AB corresponding to AD, AB corresponds to AD, is 7 over y plus 7, and this equals the known ratio. Cross multiplying, and we have y equals 1 3/4. This completes question 1. In the second sum, we must first prove that triangle ABD is similar to triangle AGE. As we can see here, we have a pair of corresponding angles ABD corresponding to AGE and ADB corresponding to AEG. Therefore, triangle ABD is similar to triangle AGE because we have a pair of corresponding angles. AA. In the next part, we must find the ratio BD over GE, which is 4 plus 2 and 2, 7 over 4 plus 7. This simplifies to 4 over 7. And this happens to be the known ratio as well, because it is formed from a pair of corresponding sides. And we use this ratio to find the next length AD. The corresponding sides to AD, as seen from the arrangement, AD corresponds to AE, which is equal to the known ratio, which is 4 over 7. Now, AE is made up of AD plus 3. Therefore, to find AD, we first cross multiply and simplify to find AD, which is equal to 4 centimeters. This completes question 2. Question 3a. State the triangle similar to triangle XYW. As you can see, we have corresponding angles here. Therefore, triangle XYW is similar to triangle XZV because of two corresponding angles. Next, we want to find the length of YW. We must first find the known ratio from the pair of known sides, which are corresponding. XY, which corresponds to XZ, gives us the known ratio, which is 8 over 11. Now, the corresponding side to YW is ZV, and this will be equal to the known ratio. YW is what we want to find, and ZV is 12. Simplifying it, we have YW equals to 8 and 8 over 11 cm. This completes question 3. In question 4a, state the triangle similar to triangle ABC. The triangle ARQ has corresponding angles with the triangle ABC. Therefore, they are similar because of the two corresponding angles. Next, we find the known ratio from a pair of corresponding sides. These two sides are known. RQ corresponds to BC. So the known ratio is RQ over BC, which is 4 over 16 reduced to 1/4. Next, we want to find the length of AQ. The corresponding sides to AQ is AC, and this equals to the known ratio. And AC is made up of AQ plus 6. Cross multiplying, and we find that AQ is 2 cm. This is a challenging sum on similar triangles. Let us first let x be the side of the square. We can see a pair of similar triangles from which we conclude that the ratio of the corresponding side x over a equals to ag over ac. Looking at the other set of similar triangles, x over h equals to gc over ac. Now we can see that AG is actually AC minus GC. Therefore, x over A is AC minus GC over AC. And simplifying it, we have 1 minus GC over AC. And we know that GC over AC is x over h. Therefore, x over A plus x over h equals to 1, and making into a single fraction, we have hx plus ax over ah equals to 1. Factorizing out and simplifying, we have x equals to ah over h plus a. Solved. In the first sum, we need to find the scale factor of the replica, which is a smaller model of the Sky Tower in Sentosa. The scale factor is simply the ratio of any corresponding lengths. In this case, is the heights of the towers. But before we proceed, we need to make sure that the units are the same. Therefore, 110 meters is converted to 11,000 cm by multiplying by 100. If we are taking the scale factor of the smaller model, it will be a ratio that is less than 1. Therefore, we need to take the smaller length over the larger length, giving us 1 over 1000. In the second part, we need to find the diameter of the replica. Once again, we need to convert the units to the same units. In this case, it gives us 250 cm. Then the diameter of the replica using the scale factor is just 1 over 1000 of the diameter of the tower, which is 0.25 cm. In part A of the second sum, we need to find the scale factor of the enlargement. First, we need to look out for the corresponding lengths. In this case, is AB and AP. When we form the ratio of an enlargement, the ratio will be greater than 1. Therefore, we need to take the longer corresponding length over the shorter one, which is 16 plus 12 over 16. Simplifying it, we have 7 over 4, which is 1 3/4. That is more than 1. To find the length of PQ, which is the corresponding length to BC, we just make use of the scale factor multiplying by the corresponding length, which gives us 21 cm. In part B of question 3, we need to find the ratio PQ over BC. PQ over BC is the corresponding length of two similar triangles. We know that these triangles are similar because of the two corresponding angles, which are alternate angles. PQR is similar to CBR. And we now look for the corresponding lengths which are known, which gives us the known ratio. That is PR. PR corresponds to CR, which gives us 6 over 14, which reduces to 3 over 7. Now, PQ and BC are also corresponding lengths, and therefore they should have the same ratio, 3 over 7. In the second part, we need to find the length of AP. To find the length of AP, we need to find the corresponding lengths to AP, which is AB. But before we do that, again, we need to identify the similar triangles. In this case, it's triangle APQ and ABC because they have two corresponding angles. To find the known ratio, we also notice that PQ and BC are the same lengths belonging to the first set of triangles. Therefore, the known ratio is the same as the first part. PQ over BC is 3 over 7. Now we find the length of AP by forming the ratio of the corresponding lengths, which is AB. And this will equal to the known ratio, 3 over 7. AB is just AP plus 14. Therefore, we write this as AP over AP plus 14. We cross multiply to give us 7AP equals 3AP plus 42. And simplifying it, we have AP is 10.5 cm. In the first sum, we need to find the area of the smaller triangle. Since these triangles are similar, therefore, the ratio of the areas is simply the ratio of the corresponding lengths to the square. That is, L1 is 8, L2 is 2. Simplifying this, we have 4 square, which is 16. And on further simplification, we have A2 equals to 4 cm squared. As in the first sum, these two figures are similar. Therefore, the ratio of their areas will be equal to the ratio of the corresponding lengths to the square. L1 is 3 and L2 is L. So we first simplify this to 4 and take the square root of 4 is 2. Therefore, L is 1.5 cm. In the first part of number 3, we need to find the area of triangle PQR. In order to do that, we need to identify the triangle that is similar to triangle PQR. In this case, it is triangle PST, as we can see that they have corresponding angles. Therefore, now we can proceed to find the known ratio from a pair of known sides which are corresponding, which is the side PT and PR. So PT over PR is equal to 6 over 10, which we reduce to 3/5. We have learned that the ratio of corresponding areas PST to PQR is equal to the ratio of the known sides square. Therefore, we have area of triangle PST over the area of triangle PQR is equal to the known ratio square. And we know the area of PST is 24. Therefore, we can find the area of PQR, okay, which we simplify to 66 and 2/3 cm squared. Next, we need to find the area of the trapezium. The area of the trapezium is just simply the area of the big triangle PQR minus the area of PST. That is, PQR is 66 and 2/3 minus 24, which gives us 42 and 2/3 cm squared. In this sum, we need to find the ratio of the areas of triangle PHG to the area of triangle PQR. Now, these are just two similar triangles because of corresponding angles. Therefore, we need to identify the known ratio. In this case, the ratios are given in terms of P and Q. And since we have a parallelogram here, therefore the lengths of HG would be similar to QF. Therefore, now we have the known ratio, which is P over P plus Q, and the ratio of similar areas, area of triangle PHG over area of triangle PQR, is just simply the ratio of the corresponding lengths to the square. We do not need to expand it. In the first part, we need to find the length of AB. AB is this length here, which belongs to a set of similar triangles. Therefore, the first thing we need to do is to identify the similar triangles, which is ABR similar to QDR. This is because of corresponding angles. Next, we need to identify the known ratio, which is from the known sides here. That is AR corresponding to QR, which gives us 4 over 7. With the known ratio, it is now possible to find the length AB by forming a ratio of corresponding sides, AB over QD, and this equals to the known ratio. QD is 7, therefore AB equals to 4 cm. In the second part, we are looking at the triangle BRC and the triangle DRP, and we use this to find the length of BC. As you can see that these two triangles share the same side with the first set of triangles. Therefore, the ratio of corresponding sides is the same as the first set of triangles, that is 4/7. So the known ratio is the same, is 4/7. And therefore, forming a ratio of the corresponding sides BC to DP is equal to 4/7, and DP is 4. That gives us BC equals to 2 and 2/7. In the third part, we can see that the areas ARP and BRC are actually triangles with the same height as they branch out from the same point. Therefore, the ratio of their areas is just simply the ratio of their bases, which we have found earlier, which is 4/2 and 2/7, and this simplifies to 7/4. In the last part, we need to find the ratio of the areas of BRC over the area of triangle DRP. As we have seen earlier, that the known ratio is simply 4/7. Therefore, the ratio of the areas is just simply the square of the known ratio, which is 16/49. In part A, we need to find the area of triangle ABC. Once again, we make use of similar triangles, so we need to identify the triangle similar to triangle ABC, which in this case is this triangle, which is a BPQ, because of corresponding angles. Next, we identify the known ratio, which is the side BQ corresponding to the side BC, which is 10. The ratio BQ over BC is 4/10, which is 2/5. And for similar areas, the area of triangle BPQ over the area of triangle ABC this equals to the ratio of the known sides to the square. Since we know the area of BPQ, which is 8, over the area of triangle ABC equals 4/25, And simplifying it, we have the area of triangle ABC is 50 cm square. In the second part, we have these two triangles BTQ and PQC. They are triangles with the same height as they branch out from the same point. This enables us to find the area of triangle PQC. The ratio of triangles with the same height is just the ratio of the bases. That is 4/6. We do not square it because these are not similar triangles. Therefore, 8/area of triangle PQC is 2/3. And simplifying it, we will have our area of triangle PQC, which is 12 cm square. In the last part, we need to find the area of triangle AQC. Once again, we can see that this triangle has the same height with the big triangle ABC. Therefore, the ratio of their areas, AQC over area of triangle ABC, is just simply the ratio of their bases. The base of AQC is 6 and the base of ABC is 10. Since we have already found the area of triangle ABC, which is 50, therefore the area of triangle AQC is just simply 30 cm square. In the first part, we need to name a triangle similar to triangle PQR. As we can see, the triangle PST is similar to the triangle PQR as they have corresponding angles. This will enable us to find the known ratio, which can be obtained from this information, which says that PS is 3 times of SQ. That means if SQ is 1 part, then PS is 3 parts. Therefore, the known ratio, which is PS over PQ, will be 3 out of 4 parts, as PQ is 4 parts. And this will enable us to do part B, where we have to find the ratio of the area of triangle PST is to the area of triangle PQR. And ratio of similar figures is just simply the ratio of their known sides to the square, which is 9/16. In the third part, we need to find the area of the trapezium SQRT. To do that, we need to take the whole area minus the area of the triangle. To find the area of this triangle, we make use of the result in part B. Since we are given the area of PQR, we have area of triangle PST over 48 is equals to 9/16, and this works out to be 27 cm square. Therefore, the area of the trapezium is 48, that is the whole triangle, minus the smaller triangle, which is 27, giving us 21 cm square. In this sum, we are given a plan of a house with a door 30 millimeters wide, showing a real door 150 cm wide. As these are similar figures, we could find out the known ratio, which is a ratio of the corresponding widths. Before we do that, we need to convert them to the same units. Therefore, the known ratio is the ratio of the corresponding lengths, 3 over 150, which is 1 over 50. Next, we want to find the area of the whole house, given that the area on the plan is 3250 cm square. Now, in order to do that, the ratio of areas of similar figures, as we know, is equal to the ratio of the corresponding lengths to the square. This gives us an area of 812500 cm square. In this sum, we are given two similar spheres, and the radius of one is 3.5 times the other. From here, we can get the known ratio, which is 1 is to 3.5, that is 2 over 7. Next, we want to find the surface area of the larger sphere. The surface area of the larger sphere is A, so the ratio of the corresponding surface area is 64 over A, which is equal to the square of the ratio of corresponding lengths, which is the known ratio. From here, we can find the value of A, which is 784 cm square. In this question, we are given two similar cones, and one has the height 1.5 times the other. Therefore, the known ratio is 1 is to 1.5, which gives us 2/3. We have to find the height of the bigger cone, so the corresponding height in the smaller cone is h1. The ratio of these two heights equals the known ratio. Since the height of the smaller cone is 12, therefore the required height is equals to 18 cm. Next, we need to find the ratio of the total surface area of the smaller cone to the bigger cone. The surface area A1 over A2 is just simply the ratio of the known sides to the square, which is 4 over 9. Here we are given two similar prisms. We let A1 and A2 be their respective total surface areas. Before we can find the ratio of the total surface areas, we need to know the known ratio. The known ratio is work from the ratio of corresponding heights, which is 1 is to 2.5. Which gives us 2 over 5. Next, we want to find the ratio of their total surface areas, which is A1 over A2 is simply the square of the known ratio, which is 4 over 25. In the second part, we need to find the total surface area of the smaller prism, which is A1, the total surface area of the larger prism is 625, and this equals to the ratio of areas. This gives us A1 equals 200 cm square. Therefore, the total surface area of smaller prism is 100 cm square. In the first sum, we have two similar objects and we must find the volume of the smaller object. Since they are similar, the ratio of their volumes will be the ratio of the corresponding length to the cube. In this case, the smaller volume is V and the larger volume is 3.2 meter cube. And this equal to the ratio of their corresponding length, which is 23 over 46 cube. We reduce it first before we cube it. We have 1 over 8 and therefore V equals to 0.4 meter cube. We have a similar situation here where we have two similar objects, and again their ratio of the volumes is just simply the ratio of the corresponding lengths to the cube. But in this case, we are given the actual volume, and therefore the ratio of the volume is 270 over 10 cm cube. And this equal to the ratio of their corresponding lengths to the cube. Simplifying it and taking the cube root, we have 3 equals to L over 7, giving us L equals to 21 cm. In this sum, we are given the ratio of their areas. And in part A, we need to find the ratio of the corresponding heights. We know that for similar figures, the ratio of the corresponding heights to the square will give us the ratio of the areas. Therefore, we take the square root to find the ratio of heights as required, which is 3 over 4. In this second part, we need to find the ratio of their volumes first before we can find the volume of the smaller cone. The ratio of their volumes, as we know for similar figures, is simply the ratio of any corresponding length to the cube. Since the larger cone is 448 and this is 27 over 64, working it out, we have the volume is 189 cm cube. So the volume of the smaller cone is 189 cm cube. We are given the ratio of the corresponding surface areas, which is 4 over 25. And in part A, we want to find the ratio of the radii. We know that for similar figures, the ratio of their radii to the square will give us the ratio of the areas. Therefore, we take the square root to find the ratio of radii, which is 2/5. In the second part, we need to find the volume of the smaller sphere. Once again, because they are similar figures, therefore, the ratio of their volumes is simply the ratio of any corresponding length to the cube. Since the larger sphere is 625, therefore the smaller sphere is 40 cm cube. In this sum, we are given the volumes of two similar spheres, which are 270 cm cube and 640 cm cube. And in part A, we need to find the ratio of their diameters. The ratio of their diameters to the cube is equal to the ratio of their volumes for similar figures. In this way, we can find the ratio of their diameters as required by taking the cube root to give us 3/4. In part B, we need to find the ratio of their surface areas. And we know that the ratio of surface areas is simply the square of any corresponding length, which gives us 9 over 16. Here we are given the volumes of two gold spheres as 640 and 1250 cm cube. In part A, we are supposed to find the ratio of the radii. As we know for similar figures that the ratio of radii to the cube will give us the ratio of their volumes. And simplifying it, taking the cube root will give us the ratio of the radii, which is 4 over 5. In part 2, we have to find the ratio of their surface areas. The ratio of the surface areas for similar figures is just the square of the ratio of corresponding lengths, which gives us 16 over 25. In part B, we need to find the mass of the smaller sphere. As we have learned that for similar figures, the ratio of masses is simply equal to the ratio of volumes. Therefore, if the larger mass is 25 kilogram, and the ratio of the volumes, which is found by taking the ratio of a corresponding length to the cube. Therefore, we can find the required mass, which is 12.8 kilograms. In this sum, we are given two similar statues, and we are given that one statue is 4 cm while the other is 6 cm. We have to find the mass of the smaller statue. To do that, we must first find the ratio of volumes. The ratio of volumes is found by the ratio of corresponding heights to the cube. And the ratio of masses for similar figures is just the ratio of volumes. So if the mass of the bigger statue is 500 grams, then we can find the mass of the smaller statue, which is 148 4/27 grams. In question 8, we are given a locomotive and its model. We are required to find the mass of the model. To find the mass, we know first that the ratio of masses is equal to the ratio of volumes. Therefore, we need to work out the ratio of volumes, which is actually the ratio of the corresponding lengths, which has been converted to the same units, to the cube, which is 1/15625. Now we can find the ratio of masses. Mass over 72,000 kg equals 1/15625. Ratio of masses equals ratio of volumes. This gives us the mass of the model, which is 4.608 kilograms. In the second part, we need to find the capacity of the locomotive. And we know that the ratio of volumes, which is 0.85 over V, is the ratio 1/15625. And simplifying it, we have 13281.25 liters.